Hi again everyone, Chris Tisdale here again. In this presentation I'm going to do another video on complex numbers. Now in previous presentations I talked about various forms of a complex number, so the Cartesian form, the polar trig form and polar exponential form. So we're going to bring some of those ideas together now via an example where we're taking powers of complex numbers. So let me share my screen with you and we can start. Okay, so one of the motivations for using these different forms of complex numbers is that they can simplify calculations. So here we've got a given complex number z. It's -1 plus root 3i, where I, remember, is the imaginary unit, I squared equals -1. We're asked to do two things: calculate a polar exponential form of z and hence determine the principal argument of z to the power 23 and write z to the power 23 in Cartesian form. So let me just refresh your memory of what a polar exponential form is and a polar trig form. So if you plot a point in the complex plane, you can draw a line segment to the origin, you've got a distance, and you've also got an angle to the positive real axis, and the form is given here. So this is a polar trig form. Okay, and there's also a polar exponential form where instead of cos plus I sine, you've got this exponential here. Again, r is the length to the origin known as a modulus, and theta is an angle. Okay, so in this form up here, we've got the Cartesian form, and we want to go to this form. Well, we could, if we want to use these ways of going from Cartesian to these polar exponential forms, but in this case, it's pretty easy. So I'm actually just going to draw a picture for the first part. Okay, so let's draw a picture and see where this point actually lies. So it's, if I just draw a freehand, say, complex plane, it's -1 plus I times root 3. So I go 1 unit to the left and root 3 units up. Okay, so this would be my z, and say if I connect that to the origin, I've got then a special little triangle. Okay, one of these well-known triangles from trigonometry. Okay, it's a right-angled triangle. So this hypotenuse would be this orange line segment there. You've got a vertical side of root 3, you've got a horizontal side of 1, and by Pythagoras you know that the hypotenuse must be 2. So we know that the length here, the r, should be 2 units just by drawing a simple little triangle. Okay, we also know, because this is one of the basic triangles from trig, that this angle will be pi on 3 radians, and this angle will be, say, pi on 6 radians. Okay, so just by drawing a little diagram, we can actually work out what the r and what the theta should be, or the argument of this complex number z. Okay, now you could, if you wanted to go and work out, use these formulae here, but really, you know, it's not required. Okay, so from our diagram, r is 2, and say I'm going to write down the principal argument of this thing, which the capital A means principal argument, and the value in this series of videos, the value of that angle is always between -pi and pi. So I start at the positive real axis, and I want to rotate and see how much I rotate to get to z. Now I know this angle here from this triangle is pi on 3, so what's left will be 2 pi on 3. Okay, so hence z equals r e to the I theta, and it's just 2e to the 2 pi I on 3. So there is a polar exponential form for this complex number. Okay, and in fact it's a simplified form because the angle with it is associated with it is between negative pi and pi. Okay, now there are lots of answers here because you could keep rotating and rotating and rotating. So if you add any multiple of 2 pi to this angle, you'll get back to the same place. So there's not just one answer for this particular A, but there is a simple answer if you like. Okay, let's have a look at the second part. Determine the principal argument of z to the power 23 and write z to the power 23 in Cartesian form. Now, in this question, I'm going to assume that you can leave powers of real numbers unsimplified. Okay, that just means we have to do one less calculation. Okay, so z to the 23. Well, you could put brackets around there and, you know, have a massive Pascal's triangle and do it that way, but no, they want you to do it using this polar exponential form. Okay, so it's 2e to the 2 pi I on 3, all raised to the power 23, and we can just use our power laws, if you like, or index laws. Okay, so if I multiply this or distribute this 23, it'd be 2 to the power 23 times e to the 23 times 2 times pi I all over 3. So 23 times 2 is 46. And what I would like to do is simplify this power so that we get it down to something between negative pi and pi. Okay, so one way to do that is to break this down into the following. This is not the only way to do it. Okay, so 46 over 3, that is 15 and 1/3. Okay. Okay, 15 and 1/3 pi I. So what does this tell me? Well, it tells me that I go 15 half turns, if you like. So that's pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7, etc. up to 15 pi. I'll get over here. And then I go an extra pi on 3. Okay, so I'm actually going to end up somewhere around there with this complex number. Okay. So what is this in terms of angles between pi, a negative pi and pi? Well, it'd have to come from this side and go down 2 pi on 3 radians. Okay, so I would actually go in that way. Because I'm rotating in a clockwise direction, it's negative. Okay, so now I can actually write down the principal argument of z to the 23. It's negative 2 pi on 3. Okay, so we're happy about that. And the last thing I want to do is write z to the 23 in Cartesian form. Okay, again, we can leave these sort of powers of real numbers unsimplified. So how do we do that? Well, we're going to use the polar trig form of a complex number. Okay, so we've still got an r and a theta. It's just that we don't have an exponential here. We've got cosine plus I sine. Okay, so let's replace this with our cosine and sine. So it'll be the cosine of negative, cosine of negative 2 pi on 3 plus I sine of negative 2 pi on 3, and then all we have to do is simplify these things here and work out what they should be. Okay, well, if we're in the this quadrant down here, we know that both cosine and sine are negative in that quadrant. So both of these will be negative. And if I want to, I can basically just look at this triangle again and work with this pi on 3. Okay, so cosine of pi on 3 will be 1/2, but because it's in this quadrant, it'll be negative, and it'll be the same as cosine negative 2 pi on 3. So we'll get something like this. Okay, this will be negative 1/2, and sine of pi on 3 will give us root 3 on 2, and because we're in this quadrant here, it's negative. Oops. All right, and we can cancel off these 2's and distribute this, and it's going to be something like this: negative 2 to the 22 minus I 2 to the 22 root 3. Okay. All right, so let's recap. There's the polar form of our complex number z. All we did was draw a diagram. Okay, that would be my suggestion to you for these kinds of problems. Draw a diagram first, and then you might not have to do any calculations. Here is z to the 23, and then from that we could get the principal argument, which is always between negative pi and pi in these series. And lastly, we use the polar trig form to get back to the Cartesian form of z to the 23. It was here. Okay, so there are some calculations involving the powers of complex numbers. Now remember, the polar exponential form can help you simplify the calculations. That's one of its benefits. Now in forthcoming videos, I'll do more examples on complex numbers and these polar exponential forms. If you have any questions, any comments, you can always put them in the comment section below. So I hope you enjoyed this video, and I hope you can join me again. Bye.